Saxon's Trig, lesson 109, is about rational numbers. Now, at first glance, this feels like we are going back into elementary school or early middle school when we learned about rational numbers being numbers that either end or repeat. And somewhere along the line, you probably had a teacher who said something like, turning repeating numbers into fractions is difficult. We're not going to talk about that. Just take our word for, if it's 0.232323, you just write the rep 10 bar over the 23. And you call it a day. That's its decimal form, and your calculator might convert it to fraction for you, or just don't worry about turning it over to a fraction. All right, so now that you know about geometric series and those formulas, you can do this proof, and that's why the teachers didn't do it before, because you were not taught that geometric series and the sum of all of those. So they remind you, we just talked about rational number either ends or repeats. And then let's just jump to example 1. Use an infinite geometric series as an aid in writing 0.0023 repeating as a common fraction. So what we're going to do is we're going to write this in sort of a scientific notation. Now, scientific notation would say that the decimal should be after the very first number. What we're going to do is take it after the first set that is repeating. So this is going to be written as 23 times 10 to the 1, 2, 3, 4. And I'm ignoring the fact that it's repeating. I realize that it is. All right, and then if I did another pattern of that, so 0.002323, and I wanted to say that I'm adjusting this answer to accommodate the next part, that's adding 2 more places, which would be another 10 to the negative, I didn't write that as -4. Sorry about that. Because it went from a large number back, or the original, to a large number, it is definitely a negative, because whatever is happening to this one, if you're making it small, it's negative. And same thing here, then I'm making it smaller by another 2. So that's another -2 added. And then if I added another set, I would have another 10 to the -2 added to that. So now that we kind of understand our basics here, we're going to take our formula a sub 1, which is, for us, we said it was this, so 23 times 10 to the -4th over top of 1 minus the common ratio. Well, what was the common ratio each time? It's this 10 to the -2nd. So at this point, they change that over to a decimal and they call it 0.01. So 1 minus that is going to be 0.99 for the denominator. And there is no change to that 23 times 10 to the -4th. Okay, now this is not a fraction that I can use as an actual fraction because my numerator is in scientific notation. So how would I get rid of this 10 to the -4th? Well, if I multiply both the top and the bottom by 10 to the 4th, sorry, I'm kind of cramming that in there, then this 10 to the -4th and 10 to the 4th is going to become a 1, or basically be crossed off. So now my numerator is just the 23 over top of 0.99 times 10 to the 4th. That means I'm going to move that decimal 4 places, using up 2, getting past the 0.99, and then filling in the other 2 holes with zeros. Oh, there's the fraction 23 over 9,900. That actually is what 0.023 repeating means. Okay, example 2. Use an infinite geometric series as an aid in showing that 5.013 with the 013 repeating is a rational number by writing it as a common fraction. So again, we're going to begin with, and they're going to ignore the 5 and keep it as a whole number. So we're going to consider that as 5 plus. And then this number would be 13 times 10 to the, and how many places did we move that? That would be 1 to -3. Pause for just a second. I paused it there because the book decided to not do this example in scientific notation. They decided to do it in decimal. So I'm going to come back and do it in the decimal format as well, but continuing here, and I went ahead and filled in that there are 3 numbers repeating every time. So that's why I have a 10 to the -3 as my repeating common ratio. So just like before, but I have a 5 carrying in front of me. This has the 13 times 10 to the -3, and this has become 1 minus 0.99, no, 0.00, goodness, 1. 1 minus that is 0.999. My brain keeps getting ahead of me there. And then want to fix this part by multiplying by 10 to the 3rd over 10 to the 3rd. So I still have that 5 carrying in front plus the 13 over 999. Now I can't leave that way. I still have to give this a common denominator and multiply that by 5. And they're telling me that's 4,995. I knew I couldn't do it in my head. Plus the 13 should give me a total of 5,008 over 999. Okay, now to go back to their decimal, instead of writing it in scientific, they kept the 5 separated. And then they said that their top, the first A sub 1 is 0.013. And then they get that same 1 minus, and it's still 3 things, so it's going to be the 0.999. And then they moved the decimal 3 places, both top and bottom, giving them 5 plus 13 over 999. You're getting to the exact same place, common denominator, and then get to your answer. So whether you do it in scientific or in decimal, either way, at some point, you're moving it 3 places. And so if there had been, let's say 0.9999 in the bottom, you would have had to have moved both 4 places, and then that would have become 130. So it's whatever the biggest amount is. And then I'm checking their wording here. Seems reasonable to induce from the results of the preceding 2 examples that when we have 2 digits that repeat, the common ratio is 10 to the -2nd. Yes, and when we have 3 digits that repeat, the common ratio is 10 to the -3rd. And then when we have 4 digits that repeat, the common ratio is 10 to the -4th. And hopefully you picked up on that as we did it, but if not, they were just clarifying that you definitely have that.